In this tutorial, we'll look at some common questions in the topic of chemical bonding. Now, a chemical bonding question that is guaranteed to come out in any exam would be to draw a dot and cross diagram. Okay, so it's very important for you to be able to draw a dot and cross diagram for a covalent compound, a covalent substance, and an ionic compound. With that, we have looked at the steps. We have gone through the steps in the lessons. Let's very quickly review it for two other substances. The first of which is hydrazine. Now this question again is very kind. In view that hydrazine is a complicated molecule, they have actually provided a hint in the form of this line over here. Okay, if you can recall, in representing the structures of covalent substances, a line tells you that there is a covalent bond between the two nitrogen atoms. Okay, so from the question, it already tells you that the two nitrogen atoms are sharing one electron each with each other. Okay, so that will help you with step number 4. Okay, so let's quickly run through the steps. First, we list down all the atoms. We have 4 hydrogen atoms. We have 2 nitrogen atoms. Step number 2, to write out the electronic configuration for all. Step number 3, to determine the number of electrons each atom needs to share. Okay, and then step number 4 is to find a suitable arrangement for sharing such that the sharing needs are met. So in this case, I've already mentioned that the nitrogen will share one electron with the other nitrogen. Okay, so it has already shared one of the it has already met one of the sharing requirements, so it needs to share 2 more. Okay, each nitrogen needs to share 2 more. There are 4 hydrogen atoms that needs to share 1 each. So very obviously, it will look something like this. Okay, where each hydrogen atom would share 1 more with each hydrogen atom. So once we have that, we would have met the sharing needs of your nitrogen and all your hydrogen atoms. So this would be our dot and cross diagram. Now there is still a step number 5, which is to draw remaining electrons. And what do I mean by remaining electrons? If you look at the number of valence electrons on nitrogen, there are 5 valence electrons. So after sharing 3, it is supposed to have 2 remaining, or 2 electrons that are not used for bonding. So remember, do not skip step number 5. If not, you will lose marks somewhere. Okay, so the last thing to do is to write in the legend: electron of nitrogen and electron of hydrogen. Okay, just for education purposes, remember in drawing the structure of covalent molecules, we usually represent a covalent bond or shared pair of electrons by a line, and this is the structure of hydrazine. In some higher level text, we would want to show the lone pair or the non-bonding electrons by putting 2 dots above nitrogen. This tells you that there's a pair of electrons that is not involved in bonding. Next, we will run through the steps for drawing an ionic compound. The ionic compound here is sodium oxide. So step number 1, list down all ions with charges. In sodium oxide, if you look at the formula and if you reverse the formula, okay, remember there was a cross multiplying technique to get the formula of an ionic compound. If you were to reverse it, you will get this. You have 2 sodium ions and 1 oxide ion. So step number 1, list all the ions together with the charges, write the electronic configuration for each ion starting from the atom. So the electronic configuration for sodium atom is 2.8.1. As we know, it's not stable, so you need to remove one electron. Okay, and then the electronic configuration for oxygen is 2.6, and again it's not stable, so it needs to take in 2 electrons to become 2.8. So once you are done with step number 2, the last thing to be done is to draw the electron arrangement for each ion. So sodium ion has the configuration 2.8. Okay, don't forget to add in the bracket the charge and the number of ions. And then oxide would have the following electron arrangement. Now do take note, very very importantly, this is a common mistake, that the non-metal atom would have taken in electron from the metal, and in step number 2 we can see that it's taken in 2 electrons. So 2 of the valence electrons in oxide ion must be of the opposite symbol. So like that, electron of sodium and electron of oxygen. Okay, in some higher level questions involving dot and cross of ions, okay, polyatomic ions, this is not strictly within the O-level syllabus, but should such questions ever come out, like the previous question, they will give you a hint in the form of lines. So for example, if you are asked to draw the hydroxide ion, they will give you the following structure in a question. Or another one would be chloride ion. Okay, so if you are given something like this, don't be alarmed that it's a polyatomic ion. Just take note that there is a line between the atoms, and the line tells you that there's a covalent bond between chlorine and oxygen, between oxygen and hydrogen, so they are sharing one electron with each other. Other than drawing dot and cross diagram, type of question that will come out in any exam would be to explain properties using structure and bonding of the substance. So over here we are looking at magnesium chloride. Magnesium chloride is an ionic compound. So the question is asking for why is it that solid ionic compounds do not conduct electricity, but it does when aqueous or molten. Or molten is from lessons. In this question we are just looking at aqueous. Okay, so a very complete answer would be this: in order for a substance to conduct electricity, it must contain mobile charged particles. So in solid state, the ions are held in fixed positions. If you have the time, you can mention by very strong electrostatic forces of attraction. Therefore, they cannot move, or they are not mobile, so they cannot function as charge carriers. But in aqueous state, the forces have been overcome, the ions are mobile, so therefore they can serve the function of charge carriers. So as seen in the mark scheme given by Cambridge, is very very lenient. You just need to say in solid ions cannot move, in aqueous ions can move. But I think in answering such questions, it's always a good practice to mention that in solid state the ions can only vibrate about fixed positions, so they cannot move and cannot serve as charge carriers. Whereas in liquid or in molten or aqueous states, the ions are mobile, they are free to move, so they can carry charge. Next, we are looking at identifying the properties of hydrogen chloride. So the first thing is to be able to come up with the structure of hydrogen chloride. Hydrogen chloride is made up of hydrogen and chlorine. They are both non-metals. So we are looking at a covalent compound. And for covalent compounds, most of them have simple molecular structures or simple covalent structures. And the next thing we need to be able to recall is that substances with simple molecular structures, they usually have low melting point and boiling points. Okay, they actually usually do not conduct electricity in any state. Okay, however, this question is tricky because we are looking at hydrogen chloride. Remember, there are certain exceptions where the covalent substance can actually react with water and to form ions, and hydrogen chloride is one of them. The other one would be your ammonia gas. So when it is put in water in aqueous solutions, it actually ionizes, it forms ions, and then it becomes a conductor of electricity. Okay, so with that, if we analyze the four options, we know straight away that C and D is out because the melting points are quite high. So then to evaluate whether A or B is the answer, we need to look at the electrical conductivity. In aqueous solution, your hydrogen chloride is actually a conductor. Okay, so when hydrogen chloride dissolves in water, essentially it becomes hydrochloric acid. Again, we look at another question where we are supposed to identify the explain for the properties using structure and bonding. And when you see a diagram like this, hopefully it will come to your mind that we are looking at giant covalent or giant molecular structures. Okay, the question is kind to tell you that boron nitride resembles the two allotropes of carbon. When you first see boron nitride, you may be taken aback because we don't learn that in the syllabus. But once you see the diagrams and the question also tells you that it resembles that of carbon, you should be able to immediately link structure A to that of graphite and structure B to that of diamond. Okay, when a compound has a structure similar to graphite, it would have the same properties as graphite. When a substance have the same structure as diamond, you would have the same properties as diamond. So whatever explanations that applies to graphite would apply to structure A. Whatever explanations that applies to diamond would apply to structure B. So very quickly for part A, why boron nitride with structure A can be used as a lubricant, the answer is the same as why graphite can be used as a lubricant. So just change graphite to boron nitride. So there are weak intermolecular forces between the layers. Okay, so when a force is applied, the layers can easily slide over one another. Now a key word over here is that the layers slide, not the atoms. The individual atoms are held in rigid hexagonal rings. So it's the entire layer that slides when a force is being applied. That's why it's slippery. For part B, why boron nitride with structure B does not conduct electricity, the explanation is the same as why diamond do not conduct electricity. So you just have to mention that all the electrons are used up for bonding. Okay, so there are no free or no mobile electrons to act as charge carriers. For part C, why boron nitride with structure B can be used in cutting tools and drill bits, the explanation is the same as why diamond can be used in cutting tools and drill bits, which is also the explanation for why is diamond strong. So you have to mention that it has a giant molecular structure. Okay, a lot of energy is required to break the numerous, if you take a look in the structure, there are numerous strong covalent bonds. Each line over here represents a strong covalent bond. Okay, so there's a network, there's a three-dimensional network of strong covalent bonds that needs to be broken for structure B to collapse. So it's very, very strong, and therefore it can be used as a cutting tool or drill bit. Once again, in the next slide, I will show you the marking scheme given by Cambridge, and I will highlight the important keywords that you need to have in your answer. So as mentioned, why is graphite soft and slippery? You need to mention that there are weak electrostatic forces, weak intermolecular forces between the layers. Okay, so therefore the layers can slide when a force is applied. Take note that Cambridge will not allow that atoms can slide. Okay, so the other parts for part B and C, the answers are very much similar to what I have given you earlier. Next, we go on to look at structure and properties related to metals. So over here we are looking at magnesium. They require you to state two properties that are characteristic of most metals. Okay, so metals have a variety of physical properties. Some of them are the same as ionic compounds. Okay, for example, when we say that metals have high melting point, boiling points, is that unique to metals? The answer is no, because ionic compounds have high melting points and boiling points as well. Giant covalent molecules have high melting point, boiling points as well. So what properties are unique to metals? That would be things like shiny, malleable, ductile. Okay, and most importantly, this property it applies for all metals, which is that it conducts electricity in the solid state. Okay, the question below, we are looking at aluminium. Again, is a metal. We need to explain why aluminium is malleable. Now the answer given by Cambridge, it goes something like this, that the atoms have an ordered arrangement, are orderly arranged in layers. Okay, so when a force is applied, the layers can easily slide over one another. Okay, that's why metals are malleable. But personally, I don't think that's the best answer you can give, because the opposite of malleable is brittle. Okay, so when you heat an object that's malleable, it doesn't break, it just changes the shape. When you heat an object that's brittle, it breaks apart. So why is it that metals are malleable? It's because when you displace the atoms, the metallic bonds are not disrupted. For me, that is a more correct answer, that the metallic bonds are not disrupted, or the electrostatic forces of attraction between the metal cations and the sea of delocalized electrons are still present. Okay, and this phenomenon is due to the electrons being mobile. All right, the delocalization of the electrons in the giant metallic lattice structure. So as mentioned, these are the marking points given by Cambridge. If you wish to be safe, you might want to add on the point that the metallic bonds are not disrupted when we describe why are metals malleable. Next question, we look at how structure and bonding affects the melting and boiling point of different substances. So the two substances in this question would be chlorine and sodium chloride. So the question requires us to explain why chlorine has a low boiling point and sodium chloride has a high boiling point. For that, the question already tells you to answer in terms of structure and bonding. So first thing, we need to identify the structures of chlorine and sodium chloride. Chlorine has a simple covalent structure or simple molecular structure. Sodium chloride has a giant ionic lattice structure. Okay, and then we have learned that substances with simple covalent structures have weak intermolecular forces of attraction between the molecules. So for example, what you see here, each one of them represents a chlorine molecule. So between the molecules, there's some weak attraction, and we call this intermolecular forces of attraction. Okay, whereas for compounds with giant ionic lattice structure, you have strong electrostatic forces of attraction between the oppositely charged ions. Okay, so in this case, between your sodium and chloride ions, there is strong electrostatic forces of attraction. So therefore, for simple covalent molecules or simple molecules, very little energy is required to overcome the weak intermolecular forces, whereas for sodium chloride, which has a giant ionic lattice structure, you need a lot of energy to overcome the strong electrostatic forces of attraction between the ions. Again, given the popularity of such questions in exams, let's go through one more example. Over here, we are looking at magnesium, silicon, and sulfur. Again, using ideas of structure and bonding, explain the difference in melting point and electrical conductivity between magnesium and sulfur. Okay, so firstly, structure of magnesium, giant metallic structure. Okay, sulfur has a simple molecular structure or simple covalent structure. Bonding, giant metallic structures have strong electrostatic forces of attraction between the sea of delocalized electrons and the metal cations. Okay, whereas for simple molecules, we have only weak intermolecular forces between the sulfur molecules. Okay, so once again, very little energy is required to overcome the weak intermolecular forces between your sulfur molecules, so melting point is low, whereas a lot of energy is required to overcome the strong electrostatic forces of attraction between the sea of delocalized electrons and your metal cations, so the melting point of magnesium is high. For electrical conductivity, we are looking at mobile charge carriers. So the sea of delocalized electrons in magnesium can carry charge, whereas in sulfur there are no free mobile electrons to carry charge.